let's continue. We can write delta phi as k delta x. I'm assuming that initial phase angle difference is 0. Okay, for simplicity, they don't have to be, but oftentimes they are 0. What is k anyway? K is 2 pi over lambda, right? So plug that in. Now, you want this to be equal to 2n pi, multiple of 2 pi. That's for constructive interference. Okay, maxima. Or in an odd multiple of pi, like 2n plus 1 pi. Okay, that's constructive interference. Here is destructive interference, right? Maxima and minima. I can solve for delta x alternatively. You know, instead of say delta phi equals 2n pi, I say delta x equals what? Okay, let's see here. You want 2 pi over lambda times delta x to be equal to 2n pi, right? You see, 2 pi and 2 pi cancels. What do you have? Delta x over lambda equals n. In other words, you say delta x equals n lambda. That is the condition for constructive interference, or interference maxima. Okay, what about 2n plus 1 pi? Alright, here what you need to do is you need to move that 2 pi down here, okay, and then 2n plus 1 divided by 2, and then pi and pi cancels. So what you have here is n lambda plus half a lambda, okay? That is the condition for destructive interference. Okay, let's see if it makes sense. What is n lambda anyway? Okay, that tells us for two waves to have constructive interference, in which you want them to have the same phase angle, you want to make sure that they travel a distance that differs from each other only by a multiple of wavelengths. If I draw a diagram, you will see clearly why that is the case. Okay, here is a first wave. Remember, they have the same wavelengths. Okay, they have the same wavelengths. And here is a second wave. Okay, let's use red. So here's the second wave. Okay. If they both travel this distance, they of course, when they arrive at that location, they'll have exactly the same phase. Now imagine the next wave travels further by a whole wavelength. Okay. You see, every time a wave travels further by one wavelength, that's lambda, right? Its phase goes back to itself, right? This is down, this is also down, right? Or I can add yet another wavelength, okay? You see, the phase goes back to itself. So what that means is that anytime a wave travels a wavelength, or 2, or 3, or 4 wavelengths, the phase changes by 2 pi, 4 pi, 6 pi, and so on. In other words, if it is originally in phase, it is still in phase. This is why the condition of constructive interference is the same as delta x equals n lambda. Because if they start from the same initial phase angle, and one wave travels a certain distance, and the second wave travels the same distance plus a whole bunch of wavelengths, okay, just like here, the second wave travels an actual 2 wavelengths, you will arrive at this moment, you have the exact same phase. So we have constructive interference. Alright, what about n lambda plus half a lambda? So here in this case, the second wave travels not a multiple wavelengths anymore, but in addition to that, it travels an extra half a wavelengths. Okay, so this is to say, for example, you travel half a wavelength, so instead of going all the way there, you stop right here. You see, this is down, right? But then you travel half a wavelength, you're up. Okay, because you know, when you travel an extra whole wavelength, your angle, phase angle, advances by 2 pi, right? So when you travel an extra half a wavelength, how far does your phase angle change? That will be half of 2 pi, which is pi. Okay, so you see, you have an extra phase angle of pi, which means 180 degrees, which means you have just reversed your phase. This is why, if the second wave travels n lambda plus an extra half a wavelength, you will reverse the phase from the first wave. Therefore, you have what's called destructive interference, and the result is a minimum. Okay, here is a simple example. The textbook has a numerical example based on the same diagram, but I don't think we need numbers necessarily. Just look at the idea. Okay, here's the idea. you have a pair of speakers. Okay, they are driven by the exact same amplifier, audio amplifier. Okay, so you play a song from your radio or from your receiver, whatever, CD player. Okay, that source drives speaker 1 and speaker 2 simultaneously. So speaker 1 and speaker 2 will emit identical waves. Okay, so what's the initial phase difference? That would be 0. Okay, initially they have the exactly same phase when the two waves just emerge from source 1 and source 2, both speakers. I want to know what happens at point P. Okay, you see, the idea is that the only reason why the first wave and the second wave can have different phases when they arrive at point P is not because they have initial phase difference. They don't. Okay, but rather it's because the second wave might have traveled different distance compared with the first wave. Okay, so can you find the condition such that this point P will have a greatest amplitude of sound? In other words, construct interference of the two waves? Well, very simple. All you have to do is to draw this line here, measure its length, and you draw that line, measure its length. What is the difference between these two? That is delta x. Okay, delta x. That's x2 minus x1. All right, if that delta x is equal to 0, which means you're right in the middle, then these two waves will arrive at that point in phase. Okay, the phase angle differs by 0 degrees. All right, so therefore, right in the middle, you can have a maximum of sound intensity. All right, and then suppose you go up, up, up this way. Okay, you move this way. At some point, you find that the intensity becomes 0. You cannot hear anything. Why? Because at that particular location, x2 minus x1 happens to be such that the phase difference is 180 degrees, or pi. So what did that tell you? Use this condition. Okay? It means x2 minus x1 equals half a wavelength, or half a wavelength plus 1 wavelength, or half a wavelength plus 2 wavelengths, and so on. Okay, so that will give you locations for minimum. So in general, what you do is, suppose you walk along this line. Okay, you walk along this line, right in the middle. That's maximum, that's guaranteed. And then over here, you have a minimum. Over here, you have a maximum, and then your minimum, maximum, and so on. Same thing happens when you walk backwards in the other direction. Okay, you have minimum, maximum, minimum, and so on. So it alternates between maximum and minimum. So this tells us that when you listen to stereo broadcasting, okay, with two identical speakers, to be safe, you just sit right in the middle. That's where you place your couch. Okay, if you want to go forward this way or backward this way, chances are sometimes you hear maximum, sometimes you hear minimum. Okay, but of course, there is one condition, and that is the position of maxima and minima depends on the wavelengths, right? Because you want to make sure that delta x, which is x2 minus x1, equals either multiple wavelengths or multiple wavelengths plus half a wavelength. So it has to do with wavelengths. So this particular location, for example, could be a minimum for a certain frequency or certain wavelengths, but it may not be a minimum for another frequency. So you see that? So what that means is that if you're listening to music, which is of course not a single frequency, otherwise you listen to a tuning fork, right? It's made of different frequencies. Now it is possible that when you sit here, you find that the music sounds a little funny because it is missing 500 hertz. Why? Because the wavelengths corresponding to 500 hertz, it's such that it happens to satisfy the condition for destructive interference at that particular location, which means x2 minus x1 equals half a wavelength at that location for that particular frequency. Okay, so the frequency of 500 hertz will be missing when you listen here. And when you go over there, it is possible that maybe a different frequency might be missing, and so on. Okay, so you see, it's very important to know where you should position the speakers, okay, and position yourself when you want to listen to something. Of course, right in the middle, that's always the safest place to be. When you deal with a listening room, okay, the design of the room, the specs of the room, the dimensions, and the locations of the speakers, locations of the seats. These are all very important because you have to deal with interference of sound waves. Okay. The thing is, sound waves, look at the typical wavelengths of sound waves. We're looking at maybe, centimeters to meters, right? That's a typical, that's the typical wavelengths of audible sound. And that is comparable with the dimensions of a room, it's comparable with the dimensions of the human body, and so on. So therefore, it makes a difference where you sit. It makes a difference where you position the speakers. Okay. Now, we don't have to worry about that for light, for example. Okay. You have one light source here, another light source here. Do you ever worry that as you move on, you're gonna see total darkness and bright and dark? No. You never worry about that. And the detailed reason will be studied in optics. But what is the biggest reason? Simple. The biggest reason is that the wavelengths of visible light is very, very, very short. We're looking at of the order of half a micron. Okay, 10 to the negative 7 meters. So even if there were alternating maxima and minima, they will alternate so quickly, the distance, we're talking about a fraction of a millimeter. There's no way that our eyes can discern that kind of difference. Okay, so when it comes to designing acoustic environment, okay, a listening room, auditorium, the interference must be taken into consideration. But when it comes to designing lighting, you don't worry about that. Okay? All right, now let's look at a special application of the superposition of two traveling sinusoidal waves. In this case, we look at two sine-cosine waves, simple harmonic waves. They have, for simplicity, the same exact amplitude, okay, same exact amplitude, same exact frequency, and wavelengths. The only difference is that one wave travels along the positive x direction, look at the negative sign here, and the other wave travels along the negative x direction, look at the positive sign here. Okay, so you got one wave going this way, right? One wave going that way. Can you think of an example? Well, how about this? How about if I have a string attached to a wall, right? Attached to a wall. And then the other end of the string, I hold it and I wiggle it like this, right? So you send a pulse going down, right? Now when the pulse meets the other end, meets the wall, what is it going to do? Well, it's got no place to go further, so it bounces back, right? So you see, you got an incoming wave and you got a reflected wave. Okay? When we want to travel to the right, the other way we want to travel to the left. Let's say, suppose they have the same amplitude as well. Okay, you add them together, what is going to happen? Well, you see, you got two waves of the exact same strengths. They are identical except they travel in opposite directions. When they meet, do you still believe that the resultant wave is a traveling wave? Well, if it's a traveling wave, then tell me in which direction would it travel? You want to go this way? You want to go that way? You see, these two waves are identical. They have the exact same strengths, right? So it makes no sense to say that when you add them together, the resultant wave is going to go this way or that way, because that breaks the symmetry between these two waves. So the only possibility is that you don't get a traveling wave anymore. Okay, you got a wave pattern that no longer propagates either to the left or to the right. Rather, it is a standstill. We call it a standing wave. Now, this doesn't mean there is no oscillation going on. Okay, what it means is that the oscillation pattern is such that if you follow the location of a wave crest, you find that crest is always there. Okay, it never moves from place to place, in which the wave pattern never travels, even though there's still an oscillation going on. Okay, let's look at how we add these two waves up. So here's wave 1 traveling along the positive x direction, wave 2 traveling along the negative x direction. I need to add y1 and y2 up according to the superposition principle. How would I do that? Well, I would need a formula which adds two sine functions up. Okay, two sine functions up. In fact, I wrote a formula here, but that formula is not quite relevant here. What I need to know is what happens when you add sine alpha and sine beta. This is alpha, this is beta. Alright, let's see what happens. You remember, this is 2 sine what? Alpha plus beta over 2. And then cosine alpha minus beta over 2. So there's a typo here. Okay, it should be sine alpha plus sine beta, not sine of alpha plus beta. All right, in our case, again, this is alpha, and that is beta. Okay, so we have the resultant expression for the standing wave now. Y equals y1 plus y2. Okay, let's see what happens. There's a 2, and there's an a, there's an a here. I'm going to take that a out, right? Let's see what happens. Sine of alpha plus beta over 2, alpha plus beta. When you add them together, omega t cancels. You have 2kx, right? Kx plus kx, so 2x divided by 2. So that's just sine kx. Okay, and then cosine of what? Alpha minus beta over 2. Okay, you take this guy minus that guy, right? What do you get? Well, you find kx cancels this time, so you get 2 omega t divided by 2, so that is just omega t. Take a good look at this wave. Okay, I claim that this is no longer a traveling wave. You know, what's the signature of a traveling wave? For any traveling wave of an undiminished pattern, you recall that it has to look like this. F x plus or minus vt. You recall from chapter 16. That has to be the case. Okay, whereas x and t must be combined in such a way that when you see x, it must be followed by plus or minus vt here. V is the speed of that wave. Now, look at what happens here. You have x and you have t, right? And yet, x and t are broken apart from each other. They are in separate sinusoidal functions. Okay, x is not directly followed by plus or minus vt. Rather, t goes into a different sine or cosine function. This violates the condition for a traveling wave. It is mathematically not a description of a traveling wave. And if you want to take a closer look, you can understand this better. If you focus your attention at one particular oscillator, okay, suppose this is a string with one wave traveling this way, one wave traveling that way. So we're looking at one segment of the string, okay. Before the oscillation, the string is simply flat, right? Simply flat. Now with the oscillation, let's say I want to look at this particular location x. At that location x, you have 2a sine x, sine kx. That never changes with time, right? That part never changes with time because x is fixed. Okay. Then you have cosine omega t. So what did that tell you? That means this particular string oscillates up and down, up and down, up and down. With what frequency? Well, with an angular frequency of omega. And with what amplitude? Well, here is the amplitude. Okay, this expression, 2a sine kx, that is the amplitude at location x. So you see, what you have here is a simple harmonic oscillator at that location with an amplitude a of x. What is that equal to? 2a sine kx itself. You know, this sine function alternates between -1 and +1. Okay, so if I were to plot this part, I would get something like this. And what is this again? This is the amplitude of the wave. Okay, so in particular, if you look at those points, what are these points? Those are the points where the sine kx value happens to be equal to 0. Okay, so this is x equal to 0. Okay, we'll find what that x is later, and that x and that x. At these locations, what is the amplitude of oscillation? Well, it is always 0 at whatever time. Okay, so there are no oscillations here and here and here. If you focus your attention on those points, you find there are no oscillations whatsoever. What about those points? This point, and this point. Well, this is where the amplitude a of x is the largest, which means not only do you have an oscillation, you have the greatest possible amplitude. Okay, so look at an oscillator at that location. At that location, you find it goes up and then down and up and down, and so on. You look at an oscillator at that location, that will have a smaller amplitude even though it has the same exact omega. So it goes up, down, up, down, up, down. And a particle here has 0 amplitude. Okay, a particle here, Up, down, up, down, up, down. And the next one, up, down, and so on. Okay, so here is the string at one moment. Okay, the next moment, the string might look like this. And the next moment, it could be momentarily flat. And then the next moment, it could oscillate like this. And then the next moment, it could oscillate like this. Okay, and this alternates time and again. Okay, goes up and down, up and down, up and down. Now, if you focus your attention on the wave pattern, you find that they're made of distinctive loops this time. Okay, loops. Each loop has a certain length, which we'll figure out in just a minute. But the thing is, those loops never move, right? For example, because those locations are fixed. They do not change over time. The end of each loop is where there is no oscillation. We call it a node. Node or N. Here is a node. Here's a node. Here's a node. Here's a node. Right in between the two nodes, right in the middle, you have the greatest amplitude of oscillation. That's an antinode, or A. Okay, antinode. So you find that the pattern of oscillation no longer propagates either this way or that way. Rather, you got these loops which will never shift position. Within each loop, you got strings oscillating up and down, up and down, up and down, with various amplitude depending on where that segment is. Okay, this is why it's called a standing wave. Now, how long is each loop? Well, this is x equal to 0, right? If at x equal to 0, of course, A of x equal to 0, which means you have indeed a node. Where is the location of the next node? This is where sine of kx becomes 0 again. Away from 0, what's the next angle at which the sine function becomes 0? Oh, that would be pi, right? So over here you have kx equals pi, right? So that's kx equals pi. So what's x equal to? X equals pi over k. Now remember, k is 2 pi over lambda. Okay, so that means x equals half a wavelength. Half a wavelength. You can show easily this is where x equals 1 wavelength. This is where x equals 3 lambda over 2, and so on. So basically what that tells us that each loop has a length which is equal to half a lambda, half a wavelength. Okay, this is an important result which we'll be using